Okay, so we've seen in our discussion of cryptography that more security requires longer keys. But as it points out here, longer keys means sending more information, and information costs money. In the communications industry, this is called bandwidth. You can see here that for different levels of security, you need to send more and more information. 1 bit is a 0 or a 1. So 1024 bits means I have to send 1024 zeros and ones. And you can read about these different security levels. 256 is the most secure. And these are different encryption technologies. Now, if you compare Diffie-Hellman, which we've talked about, to elliptic curve, we can see that the number of bits is much, much less. So that makes elliptic curve an attractive alternative to Diffie-Hellman. So this is the reason for considering elliptic curve. And the reason why elliptic curve has fewer bits is that the one-way function that is used with elliptic curve is more difficult to invert than the one-way function for Diffie-Hellman. So that's basically the idea conveyed with this table. The fact that the numbers for elliptic curve are much smaller than the numbers for Diffie-Hellman or RSA means that elliptic curve is a better alternative when it comes to encryption. Now, what is an elliptic curve? Well, here we go back to high school algebra. Here you have an equation of the form y squared equals x cubed plus ax plus b. Now notice this is not y, this is y squared. So you can take two roots. If you take the square root of the right-hand side, you'll get a plus or minus. So you're going to have plus or minus solutions for y. Notice that all of these curves have a plus and a corresponding minus solution. So this is not, y is not a function of x. Here we're graphing a relation between x and y. So you get a set in the xy plane. So you get different sets depending on the coefficients of the elliptic function. So they look kind of weird. You can get something that looks like a hyperbola. You can look something that looks like an egg in a hyperbola. You can get something that looks like a doorknob. So you have a variety of shapes. Now, so far this doesn't look like it has anything to do with group theory, but in fact the points on these curves can be thought of as a group, and we'll see that shortly. Now, there are some elliptic curves that are disallowed. We don't allow elliptic curves with a cusp or with a self-intersection. And it turns out that you can identify these by properties of the coefficients. If we have this form y squared equals x cubed plus ax plus b, as long as we avoid the case where 4a cubed plus 27b squared equals 0, then we can have an elliptic curve that doesn't have a double or triple root. In other words, it does not have a self-intersection or a cusp. So we make sure that we avoid this case 4a cubed plus 27b squared equals 0 when we choose our elliptic curves. So let's see how we can define a group operation on elliptic curves. Now remember, we're looking at points on the elliptic curve. So any point will have an x-coordinate and a y-coordinate. So our group elements are pairs x comma y. And not just any pair x comma y, only pairs x comma y that are on the group. Right? So the group operation can be conceived very geometrically. Here I have two group elements, which are 2 points on the curve, P1 and P2. In order to get P1 plus P2, I just draw the line joining these 2 points. And it turns out that this line will intersect the elliptic curve at exactly one other point. Now this is related to the fact that in the elliptic curve equation you have an x cubed term. Remember that if you have a cubic equations have 3 roots in general. So it turns out that when you're drawing this line, you are actually creating a cubic equation, and this is going to have a third root. Now, someone might ask, why isn't the third root imaginary? Well, I'll let you think about that, but it's based on the fact that, that a cubic equation can't have just one imaginary root. So that's going to guarantee that this line is going to give me a third real solution when I intersect it with the elliptic curve. All right. So again, we're taking P1 and P2, take the intersection with the elliptic curve. We're not quite done. Then we reflect the result in the x-axis. So we do a vertical reflection. Now you might ask, why do you do the vertical reflection? All I can say is, if you do that, it works. All right? So the group operation in summary, take 2 points on the curve, which are 2 group elements, take the line joining them, find the third intersection, and then reflect across the x-axis. All right, this diagram makes the point that sometimes 2 points that are close together may have a sum that's quite far away. So in some sense, this elliptic curve addition is a randomization operation. It can get a third point that is not obviously related to the first 2. Now notice P1, P2 prime is not P1 plus P2. I would need to reflect this across the x-axis, but that it shows that P1 plus P2 will be far away from P1 and P2. So this example shows the practical calculation or the steps that you go through in order to compute P3 from P1 and P2. Basically, given P1 and P2, they determine a line, you find the slope. It turns out that this slope all by itself determines the x-coordinate of the third point. There's this special equation that holds for elliptic curves. Also, if I know the slope and I know the 2 points, I can find the point-slope form for the line joining P1 and P2. If I know the x-coordinate and the line that the point must be on, then I find the y-coordinate simply by plugging the x-coordinate in to my line equation. Then, in the last step, in order to get P1 plus P2, you have to reflect. So that's why you have a minus y3 here. So read through these steps carefully, follow them one by one, and you won't go wrong when you're computing the sum of 2 elliptic curve points. This exercise is designed to enable you to prove this formula that gets the third x-coordinate in terms of the 2 original x-coordinates by using the 2 original x-coordinates and the slope. All right? So once I have established this equation, if I want to find x3, I simply solve this equation for x3, and I can obtain x3 from the 2 x-coordinates and the slope. So once again, in order to compute the third point, find the slope, find the point-slope formula, use the slope to find the x-coordinate of the third point, and then use the point-slope formula to find the y-coordinate, which you'll have to take the negative of because you want to reflect when you take the sum of the 2 elliptic curve points. Here are some examples where you're asked to compute these sums. Now, it turns out that in elliptic curve cryptography, we're not just adding 2 arbitrary points. What we're doing is we're going to take 1 point and repeatedly add it to itself. If you remember in Diffie-Hellman, we found a generator of the group of units, of multiplicative units mod p, and we took that generator and we just kept adding it to itself, and we used the discrete exponentiation operator to do the encryption. So we're going to use the analog of discrete exponentiation, except with the elliptic curve. We're going to take 1 point and repeatedly add it to itself, and that's going to be the basis of our encryption. Now in this case, we don't have 2 different points, so we can't find the line joining 2 different points. Instead, we're going to find the tangent line. So the picture is here. If I want to take P1 and take 2 times P1, I have to take this tangent line. There's a double root here. I find the third intersection, and then I reflect. In this case, there's going to be a different formula for the slope, and you actually find the slope using calculus, and that's this exercise here. Here's the formula here. So in this case, what you'll do is you'll find the slope, you'll find the point, and you use the same formula as before to find the x-coordinate of the doubled point, only in this case the 2 original x-coordinates are the same. So instead of minus x1 minus x2, we have minus x1 minus x1, which is the same as minus 2x1. All right, so again, the way you do point doubling is you find the slope, use the slope to find the x-coordinate of the result, and then use the point slope formula for the line to find the y-coordinate, and then negate the y-coordinate. All right, so practically we know how to compute doubled points in elliptic curve. Now, there is one exceptional case when adding points on an elliptic curve. Suppose I take 2 points on the elliptic curve that are directly on top of each other, like these 2 points here. Then if I draw the line joining them, then it goes straight up and down. In fact, it doesn't intersect the curve anywhere else. This is called intersecting at a point at infinity. We just mathematically create a point at infinity. We've done this kind of mathematical creation before when we created the imaginary number I. Now, it turns out that when we do this, we get everything works out very consistently. So our elliptic curve actually consists of this curve that you can graph plus a single point at infinity. Now, there's not a point at plus infinity and minus infinity. There's just a single point. You can think of this as the same point. You can say that this line up and down, the line way out here wraps around and comes in down here. So the point at infinity is a single point. And whenever you take a point on the elliptic curve xy and add it to x minus y, you're going to get the point at infinity. So we've defined a plus operation. We haven't talked about identity or inverse, so that's where we go here. So if we want to show that this actually gives me a group, this elliptic curve plus the plus operation gives me a group, I'm going to have to show identity, inverse, and associative. We've already shown closure. We've shown that if you add 2 points, you will get another point on the curve. So that's okay. But this point at infinity is actually giving me the identity. Look at this graph here. If I take the point P and add it to the point at infinity, what that would mean is I would take the point P, draw the vertical line through P, find the intersection, and then reflect. Well, if I take the point P, take the point at infinity, and draw the vertical line, it will intersect at the reflected version of P. When I reflect, I get P back again. So look at that diagram. Convince yourself that, in fact, the point at infinity is the identity. P plus infinity gives me P again. On the other hand, if I want to find an inverse, well, if I take any point P, if I take its reflection in the x-axis, if I add those two together, I'm going to get a vertical line, which gives me the point at infinity. When I reflect the point at infinity, I just get infinity again. So the inverse of a point on the elliptic curve is the point that's reflected in the x-axis. Okay, so we have identity and inverse. Now all that's left is associative. And it turns out that to prove associative is quite difficult. There's this reference here where you have a 5-page proof. So we're not actually going to do that in this chapter, just to know that the group can be proven to be associative. That's quite interesting that usually associative is the easier thing to prove. In this case, it's quite difficult. So the upshot is we do have a group. Now, whether it's abelian or not, that's up to you to show in this exercise here. All right, now so far we've talked about elliptic curves as a continuous group. Of course, a curve is a continuous set in the plane. And in the next section, we'll talk about how to turn this into a finite group, because when we're dealing with computers, we want to deal with discrete numbers and finite groups. So that's for the next video.